Now we proceed to find out the equation of the tangent to an ellipse at some given point on the ellipse. Right? So as shown here in the figure, let's consider a standard ellipse whose equation is given to us and some point x1, y1 on the ellipse. Okay, so it's given that the point lies on the ellipse, and suppose we draw the tangent at that point to the ellipse. We have to find out what's the equation of that tangent. Now here we use the general procedure of derivatives, because we know that a derivative of a function geometrically represents the slope of the tangent to that particular function. So therefore let us differentiate the equation of the tangent with respect to x. So what we get is 2x upon a square plus 2y dy by dx upon b square is equal to 0. Okay, so on cancelling 2 and on bringing the dy by dx term on one side, what we get is dy by dx is minus b square x upon a square y. So that gives us the slope in general to the tangent at any given point. So therefore, if we want to calculate the slope of tangent at a specific point given to us, which is x1, y1, what we'll do is precisely we'll replace the x and y terms with those coordinates. So we'll get the slope at the given point is minus b square x1 upon a square y1. Okay, so that's the slope of the tangent, and the point that lies on the tangent is also known to us already. So therefore, using the slope point form, we can write the equation of the line as, that's the tangent. So therefore, equation of tangent is y minus y1 is equal to m, that is the slope, so which is minus b square x1 upon a square y1 into x minus x1. Alright, so on simplifying this by cross multiplying the terms and simplifying, we get x1 upon a square plus y1 upon b square is equal to x1 square upon a square plus y1 square upon b square. Now if you look at the right hand side, we will immediately come to know that since the given point x1, y1 lies on the ellipse, so it is definitely going to satisfy the equation of the ellipse. So therefore the right side is nothing but equal to 1. Correct? So therefore we can replace the right side with 1, and hence we get the final form of the equation of tangent as x1 upon a square plus y1 upon b square is equal to 1. So that's the equation of the tangent in Cartesian form. Now it's very interesting to note about this equation. What has happened is, if you compare this equation with the equation of the ellipse, okay, what has happened is the x square term has changed to x1. So what we can visualize is x square, suppose we write it as x into x and make one of the x as x1. Okay, so we'll get that particular term in the equation of the tangent. And similarly, y square can be imagined as y into y, and one of the y is made as y1. So that gives us the second term. Okay, so that's how we get the equation of the tangent at a given point on the ellipse. We can also write this particular equation by bringing 1 on the left side, so that we'll get some expression which we call as capital T equal to 0. Okay, so this notation we will use later also in some of the formulae. Okay, so T corresponds to the expression x1 upon a square plus y1 upon b square minus 1. Right? We have 0 on the other side. Now we can also derive the equation, or rather convert this equation which we have got into the parametric form. So let us go to the parametric form. We'll start off with the equation that we obtained at the end. So this was the equation of the tangent. If you remember, the parametric equations of the ellipse are given by x is equal to a cos theta and y is equal to b sin theta. where theta is the eccentric angle of the given point on the ellipse. So for the point x1, y1, we can of course write x1 is a cos theta and y1 is b sin theta, where theta indicates the eccentric angle of the given point x1, y1. So therefore, on replacing x1 with a cos theta, we will get x a cos theta upon a square plus y into b sin theta upon b square is equal to 1. So therefore, cancelling a and b respectively, we get x cos theta upon a plus y sin theta upon b is equal to 1. So that's the equation of the same tangent but in parametric form, because now this equation has the theta term in it.